Okay, in this lesson, we're going to introduce you to the concept of a vector. And let's go ahead and start by defining what a vector actually is. A vector is a quantity that has both magnitude, and what we mean by magnitude is size and direction. So maybe like a wind speed, to where the wind is blowing northeast at a rate of 30 miles per hour. So it has size and direction. A geometrical representation. A vector can be represented geometrically by using a directed line segment, as you see in the picture. The reason we call it a directed line segment is it has a direction, and it also, the length of it, represents the magnitude. On this vector, P, the point P right here, is what's called the initial point. And the reason it's called the initial point is that is the starting point. Or the tail. And then we have the terminal point, which is Q, and that is where the vector stops. That's at the tip of the vector. We name vectors, naming vectors. Vectors are denoted by using the vector symbol, and it looks just like an arrow. Now, sometimes you will see this one instead, to where it's just got the top part. You see that one a good bit. So either one of those symbols are fine. Vector PQ above can be named vector PQ. Vector P, which notice the P is this P right here. It might just have a P above it, or sometimes you'll have just a bold face lowercase letter. So vector P as in this one. So you can use the symbol or you can use the bold letter. Magnitude, again, a given vector or given a vector with initial point x1, y1 and terminal point x2, y2, the magnitude, which we write with this symbol right here with the double absolute value bars around it, can be found by using the distance formula. Because again, if you think about it, if we're looking for the magnitude or the length of a vector, if you have an x component and you have a y component, then the distance from here to here, that's simply the distance formula, or we can actually use Pythagorean theorem. So therefore, the magnitude of v, vector v, and you can put the vector symbol above it if you would like, is equal to the square root, and then just the distance formula. x2 minus x1 squared plus y2 minus y1 squared. So there is your distance formula. So now let's find some magnitude of some vectors. But again, instead of using the distance formula, which I will on this first one, I much more prefer the Pythagorean theorem. But the magnitude of vector AB, again, I'm going to write this just to where we get used to the symbol. The magnitude of AB is equal to the square root of x2 minus x1 squared. I'm going to go ahead and subtract it as I write it down, plus y2 minus y1. Now you got to be careful. That's -2 minus -4, which would be -2 plus 4 squared. So that's going to be the square root of 225 plus 4, which is the square root of 229. And that answer is fine, or it's somewhere around 15.13 if you want to put the approximate answer. Either one of those are fine. Again, instead of doing that, I like the Pythagorean theorem instead. So to find the magnitude of vector RS here, why not do a squared plus b squared equals c squared? So the square root of the distance from here to here, the distance from 10 to 6 is 4. So 4 squared plus the distance from -3 to 5 is 8. So 4 squared plus 8 squared. Much easier. So that's going to be the square root of 16 plus 64, which is equal to the square root of 80, which that does simplify. We can break that into root 16 times root 5. So 4 root 5 would be fine as an answer, or you can write it as a decimal. That would be approximately 8.94. So either one of those answers are fine. Again, the magnitude here, find the distance from 6 to -9. That'd be a distance of 15. Find the distance from -8 to 2. That's a distance of 10. And simply do the Pythagorean theorem. And since that will equal c squared, to get rid of that squared, you're going to square root that in the end. So the square root of the two distances squared, that'll be the square root of 225 plus 100, which is the square root of 325, which that will simplify. We can break that into I know there's a root 25 in there, so there are, let's see, 4, 8, 12, 13. So we can split this into the square root of 25 times the square root of 13. So that's one answer. Or you can give the decimal answer, which is approximately 18.03. Number 4. Again, Pythagorean theorem, the distance from -5 to -7 is 2. The distance from -1 to -6 is 5. So you have 2 squared plus 5 squared equals c squared. So take the square root to find the distance. That'll be the square root of 4 plus 25, which is 29. That will not simplify. Or you can write that as approximately 5.39. Let's stop at this point and define what we call a zero vector. A zero vector is any vector that has a magnitude of 0. So just any vector with no length. Okay, now, next part, let's talk about the types of vectors. First off, we have parallel vectors. Parallel vectors have the same or opposite direction. They don't have to be going in the same direction, but not necessarily the same magnitude. So they go in the same direction or the opposite direction because we know that if they were to go in opposite directions like this, they would still be parallel. They would never touch each other. So let's come right here and just draw another picture. They do not have to have the same magnitude. So you might have something like this going on like this, to where this is vector A, this is vector B. So therefore vector A here would be parallel to vector B. Next up, you have equivalent vectors. Equivalent vectors have the same magnitude and direction. So you've got to be really careful there. So if you had a vector M, maybe, and then over here another vector N, now they have the same direction. Notice they're both traveling in like a northeast direction, identical direction. So here your vector M and vector N are the same or equivalent vectors. And then lastly, you have opposite vectors. They have the same magnitude, but they're in opposite directions. The opposite of a vector A is written as a negative A. So let's look at that. So maybe you have a vector A that looks like this. And I didn't put my vector symbols over here. And then you have a vector negative A, which looks parallel. They are parallel, but is traveling in the opposite direction. So that's what negative A would look like. So those would be opposite vectors. So maybe I should put it like this. Let's call this B. That way I can say that vector A is equal to the opposite of vector B. They're opposite vectors. Okay, next up. Use the graph below to classify each pair of vectors. So let's find vector A and vector E. So vector E is located here. Vector A is located here. Now it looks like, and you can check it with slope, you rise 1, run 2, go down 1, over 2. These vectors are parallel to each other, but they're opposite. And also the distance, the length of them are the exact same length. So these would be opposite vectors. And not only opposite, we could say that they're parallel, because I do want to remind you that the same or opposite directions, but not necessarily the same. So these would be opposite and they'd be parallel, but to be more exact, we'll just call them opposite. So now let's find I and F. Here is I. Vector F is here. Looks like you can check your rise and run to check for direction. 1, 2, 3, 4, 5, 6, and 2. 1, 2, 3, 4, 5, 6, and 2. So these are parallel vectors. They have the exact same length, so these two vectors would be equal vectors. Vector D and E, let's find D and E. Here is E, and here is D. Looks like they're going in the same direction, but they're not the same size. So therefore, those two vectors would be parallel because they are going in the same direction. B and G, here is B, and here is G. There's not really much special about those. They do not have the same direction. It looks like they might have the same magnitude. We can check that with Pythagorean theorem, but that's it. So therefore, we're going to put that they have no special relationship. And then finally, C and H. Let's find C, which is right here, and then H, which is right here. Rise and run is both 3 and 1. They're going in opposite directions. However, they do have the same length. So therefore, those two vectors would be opposite of each other. And next up, we're going to prove vectors are equivalent. Now, equivalent vectors or equal vectors, remember, they have the same direction and the same magnitude. So you can show that two vectors are equivalent if they have the same magnitude, same direction. To find out if they have the same magnitude, we are going to use the distance formula. To figure out direction, we're going to use the slope formula. So let's determine whether AB and CD are equivalent. Now, they don't have to be in the same spot. They just simply have to be pointing in the same direction and have the same length. So let's see here. So let's start with vector AB, and let's find a magnitude and let's find a direction. So a magnitude, again, we're going to do the square root. So the magnitude of AB is going to be the square root of the distance from -7 to 3, which is 10 squared, plus -6 to -2 is 4 squared. That's going to be the square root of 100 plus 16, which is 116. And you do not have to simplify that because honestly, we're just seeing if it's the same as the other vector. Next, we're going to find the slope of vector AB. So I'm going to put let's just do slope. Let's just write slope out in front of it. Slope of AB is going to be, if you don't remember your formula, it's y2 minus y1. So that'd be 10 over x2 minus x1. That's -2 plus 6, which would be 4. So it's going to be 5 halves. So now let's check the exact same two things with CD over here. So first off, the magnitude of CD. Again, it's going to be the square root of, find the distance from -10 to 0, which would be 10 squared, plus the distance from 2 to 6 would be 4. So that's going to be 100 plus 16, which is 116. So notice they do have the exact same distance. Now let's find the slope of AB, or excuse me, of CD. That's going to be y2 minus y1, which is 10, over x2 minus x1, which is 4. If you reduce it, you get 5 halves. So again, notice they're the same. So these two vectors are equivalent. Yes, let's actually see what the directions say to do. Determine whether they are equivalent given. So yes, they are equivalent. Next one, let's find magnitude. And I'm going to do this one a little bit different. We're going to find the magnitude first. And I'm just going to list it right here and under AB. The magnitude will be the square root of, let's find the distance from -2 to -14, that's 12. The distance from 2 to 6 will be 4. So that's the square root of 12 squared plus 4 squared is 144, and 16 is 160. And then instead of finding slope next, I'm just going to go ahead and do the exact same thing over here, because if their magnitudes don't match, then we don't have to go any further. We have the square root the distance from -8 to 4. And you can do x's first, y's first, it does not matter. -8 to 4, that's the distance of 12, plus -3 to 1, that's the distance of 4. So you get the exact same answer. So far the magnitudes are the same. Now let's check their slopes. Slope of the first one, y2 minus y1 will be -14 plus 2, which is -12, over x2 minus x1 is 4. So that's a slope of -3. Second set of points, y2 minus y1 gives me 12. x2 minus x1 gives me 1 minus -3, which is 4. Now let's double check that, because I've got a -3 and a +3. The first one is -4 plus, or -14 plus 2, which is -12 over 4. That does check out. The second one checks out as well. So therefore, these two vectors are not equivalent because they have opposite slopes. Now, one thing that we could say about these, they have the same magnitude, but they have opposite directions. So therefore, these two vectors would be opposite vectors of each other. But they are definitely not equivalent.